All right, 1994, number 1. Once again, working the concepts of momentum and energy together into one question, which, if you've noticed, is something that the AP really likes to do. Mix topics together. Okay, so they tell you that this 0.1 kilogram ball of clay hits this 2 kilogram block and it compresses at a distance of 0.4 meters. All right, so first question is, what's the potential energy stored in the spring? All right, fine, that's just plug and chug. You don't need to know a whole lot to do that. If you know that elastic potential energy is 1/2 kx squared, and they tell you the spring constant's 200, and this is compressed 0.4 meters, and that should give us 16 joules, I think. Let me see. 0.16 times, yeah, so 16 joules of energy is what's stored in that spring. All right, since K equals 200 newtons per meter. All right, now getting the speed of the ball and block system immediately after the collision is now a conservation of energy question. But we need to be a little bit careful, okay? Sometimes people aren't quite sure how to do this one, so they jump to this one and they're like, oh, the speed before the collision? Well, look, it's just like kinetic energy from the ball of clay equals the elastic potential energy, at the point of maximum compression. And that is not true. This is going to be a perfectly inelastic collision because it says the ball of clay sticks to the 2 kilogram block. And you should know that for a perfectly inelastic collision, energy is lost. Or we should say that more carefully. Kinetic energy is not conserved. Total energy is, of course, always conserved, right? But we're going to have some significant deformation of materials because it's a ball of clay. There's probably going to be some sound, all right, and then plenty of heat, which, again, that's going to be present in the ball and the block, and that's ultimately what deformation of materials gives you, usually, is heat that's being produced. All right, but that's where the energy goes. It's not going to be true that this kinetic energy here equals this elastic potential energy there. Rather, the kinetic energy after the splat is going to equal the elastic potential energy at the moment of maximum compression. Okay, so we can say that K final, and when I say final, I mean after the collision, equals US. All right, so Kf is 1/2 m, which is not 2 kilograms. It's 2.1. V final squared equals 16. Okay, so that's going to give us that the final energy is the square root of 32 over 2.1, whatever that is, 3.9 meters per second. Okay, now, velocity before the collision is going to be based on conservation of momentum. So we have mv before the collision equals m total v final, because that's what it's always going to look like for a perfectly inelastic collision. All right, m total being 2.1, v final being 3.9, and this being 0.1, we should be able to figure out the initial velocity. Wow, that's really fast. 81.97 meters per second. I can almost run that fast. No, I'm just kidding. Okay, so fine. All of that works out in a pretty straightforward manner, actually, as long as you don't make the huge misunderstanding of imagining that kinetic energy before the collision equals kinetic energy after the collision. So as long as you avoid that prime mistake, you're probably not going to have too much trouble with the first 3 parts of the question. All right, now part D is a little bit more involved in terms of the reasoning, right? So they tell you the stop is removed, and now want to know what that's going to do to the maximum compression of the spring. Is it going to increase or decrease or stay the same? Okay, so obviously if this is all done on a frictionless surface, which was the assumption that we made here, notice we didn't have to worry about things like, oh, well, friction does work as the block slows down, right? If that were the case, then, there would be a work term thrown in here, and it would be more complicated, like way more complicated. But okay, they tell us, the stop is removed, so since we're on a frictionless surface, what's that going to do to the maximum compression? All right, well, the same basic principles are still at work, right? You're going to have conservation of momentum, all right, during the whole process here, but it's sort of like a two-stage collision, all right? You have first, this collides with that, all right? And so that would go probably basically exactly the same, right? Assuming that collision is over very quickly, which it probably would be, it's probably safe to assume that the 2.1 kilograms that we have here are going to be moving along at 3.9 meters per second after the collision towards the 8 kilogram block. All right, but now the trouble is this. There's a spring between them, which means that as soon as that starts compressing, if the 8 kilogram block is not held in place, it will start sliding backwards. All right, so probably you could just say that in your explanation. You could say that the compression is going to decrease because the 8 kilogram block is now moving away from the 2.1 kilograms, right? And so therefore, you won't get the same maximum compression as it moves away, all right? So that would work. All right, now, from a momentum and mechanical energy standpoint, that's what they want you to talk about in E. So it's like, give me a more in-depth answer as to why the compression has to decrease. All right, now, explaining that would go something like this. The point of maximum compression is not going to be when the 2.1 kilograms here comes to rest, because it won't come to rest. It's going to be when the 8 kilogram block and the 2.1 kilogram block are moving at the same speed. So it would look something like this. Here it comes, 3.9 meters per second. Oh, the spring's compressing, so they're moving forwards, and here they're briefly moving at the same speed, and then they start to move apart. Okay, and so at that moment of maximum compression, you have final kinetic energy after the collision equals that does equal 16 joules, right? If you worked it out, the final kinetic energy after the collision will still be 16 joules, but it will be divided up into elastic potential energy in the spring and the kinetic energy of the system as those two blocks move along together, however briefly they happen to be moving at the same speed. Awkwardly, I'm calling both of those things K final, so this is like K super final, or fortissimo, if you prefer. No, sorry, K final, meaning at the moment where they're moving along the same speed, as opposed to the kinetic energy after the collision. So this is after the first collision. All right, and that equals 16 joules. All right, and this would be, really technically, there's a second collision that is happening, right? If the 2.1 kilograms and the 8 kilograms are moving along now at the same speed at some instant, well, that constitutes a second perfectly inelastic collision. So this would be at the moment when They all have the same speed. So same V for all objects. All right, so in order to actually work out what the maximum compression is, you would use conservation of energy, but you don't know what this speed is. Okay, but we said at that moment it's a second perfectly inelastic collision, so that means we can now apply conservation of momentum to it. Okay, and so, you could more or less do, all right, mv for the ball of clay before any of these collisions take place equals m total is now going to be 10.1 v final. And then from that, you could figure out the extra final velocity, right? And then figure out from that, therefore, what the maximum compression of the spring would be. Okay, so overall, yes, the maximum compression would decrease, and that's because some of this 16 joules of energy doesn't go into compression. Some of it goes into the motion of the 8-kilogram block. And so, therefore, there is less energy stored in the spring, which means it must have a smaller compression. All right, let's try out the third problem.